James Parker, talking about our technology here, which, I'm going to take a very broad view of what our technology is. I mean, for me, it's anything that we do that closes the gap between an engineering problem and a CFD-based solution. And so this includes our software development, research that we do, but also the support and training, in the various ways that we communicate our know-how to our customers in either through software licensing or through engineering services. Of course, this is a function 100% of the team that we have. We have a great team, and really, I think it's great that this year we're going to be able to hear from quite a few members of that team. So I've actually been in this role now 10 years, and during that time, the goals that we've had for developing the software and our technology have largely been the same. We want to close this gap, reduce the amount of time and effort required to get to a CFD-based solution, and we are, do this through a few different avenues. One, just the application fit. We're developing new product features, and to make models more appropriate for solution, and also more recently our application model development, and Shashank will be talking about that shortly. Also increasing the calculation size and the speed, GPU development. We've done a lot of work over the years in this area, but also the numerical efficiency, the underlying mathematics. Are we calculating things in the most efficient way possible? And then the usability, having an intuitive GUI that enables us to set up models quickly, minimize mistakes, and then of course the powerful post-processing that we do, partnering with TechPlot and the other tools that we provide. More recently though, kind of had another aspect of this, and this is the reduced order modeling. And we're going to be having a talk later today on that work. And what this really is doing, I think this combines all of the development up to this point, the application fit, the speed, usability, and goes from where we are delivering a CFD-based solution, and really the reduced order modeling is going to allow us to deliver a CFD-based solution space. So it's, and I have a short demonstration on that. The breadth of what we do here, I think it's well represented by the talks this afternoon. The application models, our ROM development service going to be talking about, as well as hearing from Andrew and Sam about the product and support. And I think there's going to be time for maybe some Q&A at the end, and so I'll probably jump back if there's any questions. Maybe have some others as well. Before getting to turn it over to Shashank, I just wanted to highlight a few of our recent development areas and how these apply to some of these application models. So first, the elastic dense phase collision model. This was released in version officially released in version 26, although we had kind of slipped it into 25.1.1 for use by Kairos and some others. And this model is an alternative to the kind of underlying model that was documented in Dale Snyder's 2001 paper, really how particles are interacting with the stress field. Our implementation here is based upon this paper here, a novel approach to MPPIC continuum particle models for dense particle flows in fluidized beds, with some pretty heavy adjustments for our grid and solver approach. This is something that had been in the works for quite a few years. We'd had a prototype, and it just wasn't very stable was the problem. Luckily, last year we had a few numerical aha moments. The stability is great now. The model adds in an angle of internal friction, some stick slip friction at wall boundaries, and really greatly improves the grid independence and in the dense phase. Oops, sorry, I wanted to go back. An example here is Kuiper's this bed. This is the training problem that everybody usually starts with. Using this elastic model, you get more of a wider spread here, and this was actually tuned with the ROM, and I'm going to, so more on this later. Also, I think Jared and I both were spending some time with same spouted bed data, and so, I mean, the grid independence looks a lot better than it did before. We've seen good match, and then also where the Snyder model just didn't work very well is also on these edges. We're getting actual good downward flow where sometimes we'd see that the models were more stagnant. So trisoparticles, we have a shaft furnace model, application model, but generally recommending this for pretty much any application at this point. And it's not the default yet, but I think it will be probably in our next release. Also want to briefly highlight our liquid modeling features. This is both for liquid sprays, like FCC risers, and then also liquid continuous phase models where we have solid particles, bubbles, various, coalescence breakup, mass transfer models. And we see this in our prop and transport application model, the conditioning tower that Pramod's going to talk about later today. We have a molten metal bubble column, and also generally, like FCC, I said FCC risers, ebulated bed hydrocrackers, drying, evaporation, et cetera. Heat transfer. Last few releases, we've had quite a bit of development in heat transfer. Particle-particle conduction is good for fixed bed applications, moving bed applications, as well as this wall resistance that we added. So cases where we have some ambient temperature that is affecting the results. We often see this like lab scale comparisons with they don't have great insulation and a very small diameter pipe. We can now include those effects into the model. And so like industrial CFBs for power generation, this is where we have the heat transfer is like basically the whole point. This is the wall resistances are critical there. Also, recent improvements in erosion modeling. We've added where now you can specify multiple models, different zones. And so this actually came out of watching the, I guess, challenges on the SECO project and how to, looking at so many different erosion areas and wanting to isolate models in different ways from post-processing, and we're saying, hey, okay, we think we can do this better, and so that are some features that for the next time around it should be hopefully post-processing is a lot easier to do. And then some current kind of future development areas. So we do have some beta capabilities for rotating systems. Some of this is released as like rotating gravity or this, but there are some body forces. There's an option within beta. You can turn on body forces, and so this turns it into a moving frame of reference. So this is being used, has been for like kilns, kind of auger systems, mixers, simulations on like looking at residence time distribution for liquid impeller systems. Then the last thing here I want to talk about is our reduced order modeling. Saurav's got a whole lot on this later. I'm really looking forward to that presentation. But just at a high level, I just wanted to kind of tie this back to the Kuipers and do a very short demonstration of the power that is here. So what we're doing is we're using the Barracuda data to train a reduced order model. The accuracy of this model is going to be a function of the training that is done. But I mean, we're seeing that we can get a fairly good model with fairly limited number of simulations using the method that Saurav has developed. And there's some tremendous benefits here for model tuning, optimization, and then eventually design optimization here. And this is, this is what I was talking about. We're going from a CFD solution to a CFD solution space with this. Our tool, it's in development. It's been in development for the past over the year plus. We are targeting a release later this year. Development's going very, very quickly. Quite excited about it, and so I mean, basically, we're going to get it out as soon as it's ready, because I know there are a lot of opportunities with this tool. As a brief demonstration here, going back to this Kuiper's bed. I mean, these are for anybody that hasn't simulated this. It's training day number 1 here for Barracuda training. And if you're interested, I think Friday. You can probably set up the Kuiper's bed yourself. But so this is 500 micron glass beads in a 2D bed, so it's basically 2 plexiglass sheets with a 1.5 centimeter gap in between. There's fluidizing air on the sides, center jet up the middle. And in the paper they talk about there's some asymmetry with the jet and things like this. So this is, I say, there's this time, this average voidage plot of the bed that is in this paper, but my only comment on maybe the asymmetry here is that we're gonna try to tune to improve the fit here, but we may be tuning on things that are, there's maybe some underlying experimental challenges that exist as well. But as a demonstration here, I'm going to improve the fit here by adjusting our drag multiplier and then an angle of internal friction. And so first thing I do is just ran 2 simulations here with multipliers of 1 and 2. Just looking at the initial simulations here at 1, I thought, this bed looks like everything looks a little underexpanded here, so I'm going to explore higher drag multipliers. So I went big, went up to 2, and then calculated an error comparing the volume fractions along. There's some cut lines, and there'll be a plot here in a moment where the experimental measurements taken, comparing the error against the experimental measurements here. And so in a normal situation, I draw a straight line, go, maybe I should be exploring less than 1. Maybe I need to run many more simulations. But with the ROM, I trained this ROM. It was like shockingly fast and easy to do. And then generated data from the ROM in between this 1 and multipliers of 1 and 2. We see, okay, there is some minimum here, maybe 1.5, and this is now saying, okay, this is very different from just what I would have done if I just drew a straight line. And I think I want to explain this, is what our ROM is doing, and Saurav's going to, luckily he'll explain the mathematics of it, but what it's doing is it's producing full field results here. So just as when we ran simulation with Barracuda, we get this time averaged volume fraction plot here. I compare volume fractions at different slices to the experimental data, calculate an error on this. We're doing the same thing for the ROM. The ROM is producing this full field data, comparing it, and calculating an error. So then say, okay, well, that 1.5, I'm going to test that point. And what you do, you retrain the ROM. Now we're in an active learning mode here, where you retrain the ROM. It now we said, okay, well, I got some more information. I now think there's a minimum right here around a little over 1.2. So I tested that point, and lo and behold, the ROM Barracuda simulation here matches the ROM result. So in just here 4 simulations, really 3, the 4th one to kind of check the answer, we've identified an improved drag multiplier. Then turn to this internal angle of friction. For these glass beads, I think probably like 20 to 30 degrees should be the range that we should be in. Anything above that is probably going to be, I think Ted might be pretty suspicious of if I say anything higher, or even lower than that. But here, let's test a large range here. So I ran 0 and 45, and see, this is where we have the opportunity to see more of the solution space here and go, yeah, that means 0. That's higher error. 30, it's not bad beyond that. I mean, the air's dropping a little bit, but I'm starting to get suspicious that I'm really, maybe tuning on experimental error, or there's other parameters within the model that should be explored. For giggles, I tested one more point, and we're not really doing much beyond on 30 degrees. Good situation, that's our default. That's always a win when the initial settings are right where you want to be. And that was that. So, here, this, development of this underlying ROM, allowed us to quickly examine, refine the solution space, this tool. We're still working on some interface and stuff. The underlying tool's looking really good. It's going to be fast. It's really easy to use. We're going to get this out later this year. So, in conclusion, we're doing broad technology development here in support of particle applications, CPFD. It's everything from these application models that we're going to hear from Shashank here next, new product features. We're going to hear from Andrew and Sam, and then the reduced order modeling with Saurav later this afternoon. So that there's maybe time for a few questions, or maybe I come back later when.
Yeah, I think we'll do a Q&A towards the
perfect.
end. Yeah.
All right. Well, thank you.
Thank you, Jim.